Okay, good morning, everybody. It's time to get started. So what I want to do today is we're going to put together all the information that we've been learning so far about the first derivative and the second derivative, increasing, decreasing, relative extrema, concavity. And I want to put all of that together with what we learned from college algebra about holes, jumps, displaced points, vertical asymptotes, x-intercepts, y-intercepts, all those kinds of places that we learned about in college algebra. So we're going to put all that information together and we're going to produce sketches of a graph as best we can. So we're going to start with example 1. And we want to go through first off some of the things that you want to be looking for. So the first thing that you typically want to do is you want to establish what the domain of the function is to be sure that you don't graph it over some place that's not included in the domain. So we'll look at the domain and then we'll look to see if there's any kind of symmetry in the graph. So this would be where it's y-axis symmetric, folds on the y-axis. That's when you replace x with negative x, but you get the same y value. Or that it has odd symmetry, which is origin symmetric. That's when you replace x with negative x and you get the opposite y value. So for example, in x cubed, the point 2,8 is on the graph. And if you replace 2 with negative 2, you get negative 8. All right, so that is origin symmetric. Then we want to look at the x and the y-intercepts. Then we want to use what we learned about in 4.6 part 1, which is the end behavior of the graph. What does the graph do as it goes to infinity and negative infinity? We want to talk about that. Now remember, when we do end behavior, just a quick review of what end behavior is. When we look at end behavior, we're typically going to be comparing the highest degree term in the numerator with the highest degree term in the denominator. So if we look at the highest degree term in the numerator or the highest degree term in the denominator, and we find that their powers are equal, then we know that it will have a horizontal asymptote that is the ratio of the coefficient of the highest degree term in the numerator divided by the coefficient of the highest degree term in the denominator. So that's one option. Another option is that the degree of the numerator is smaller than the degree of the denominator. Say that you have x squared in the numerator and x to the 4th in the denominator. The denominator is going to infinity much faster, on an order of magnitude faster. Therefore, it overpowers the numerator and pulls the fraction to 0. So you still have a horizontal asymptote, but it is the x-axis, y equals 0. Now we're going to take a look at one today for the first time, which is an oblique asymptote. And the oblique asymptote happens when the degree of the numerator is 1 greater than the degree of the denominator. Now it is possible to have a parabolic asymptote or something like that, where the degree is 2 greater or something. But we're only going to be looking at oblique ones where the degree of the numerator is 1 more than the degree of the denominator. Let's say the degree of the numerator is x to the 5th, then the degree of the denominator would be x to the 4th. Now, how do you find the asymptote? The limit, the end behavior will go to infinity or negative infinity, but it's going to do that by skimming along a line and using a line as an asymptote. The way that you find that is using long division from college algebra. I'm sure you're like, oh my God, long division, are we really going to do that? Yes, we have to do that. Okay. Then we will also be looking for any vertical asymptotes. Remember, vertical asymptotes are zeros of the denominator that do not cancel and disappear from the denominator when you fully factor the numerator and the denominator. Then we'll look for holes in the graph. Holes in the graph are zeros of the denominator that do cancel and completely disappear from the denominator when we have cancellation from a fully factored numerator and denominator. That information is what we have studied prior to this chapter. And then we're looking at the information about the derivatives in the shape of the graph. So then we'll calculate the first derivative. We'll find all the critical points. And we'll determine the intervals where f is increasing and f is decreasing. That will also enable us to locate the extrema points, the relative maximums and relative minimums, or depending on the graph, it could be an absolute maximum or an absolute minimum. We will also be able to find the y value at those points by plugging the x coordinate of the critical point back into the original function. And then we can look at concavity, which is the second derivative. We can also use the second derivative, since we're going to find it anyway, to do a second derivative test to determine where the relative extrema are. In this case, since we're going to be looking for increasing and decreasing anyway, we'll already have that information. So I don't think there's a lot to be gained in this particular type problem from doing the second derivative test. We will note where it's concave up, where it's concave down, and then we'll use that concavity information to locate where it changes concavity, which is when the second derivative is equal to 0, or the second derivative does not exist, but the first derivative does exist. And those are called inflection points. So we have a great deal of information to put together here. And I made sort of a, I guess, a list of shorthand of all the things that we need to be looking at. So we're starting with a really simple one. This is x minus 1 quantity squared times x plus 2. When we're looking at this one, we're going to go through each of the steps one at a time. And we have domain, and it is polynomial. Because it is polynomial, again, that's a binomial squared, which would give you a trinomial, times another binomial, which would give you a quadrinomial. So it is polynomial. And because it's polynomial, we know the domain is, what's the domain? Oh, don't give me
all
here in the
real
headlights.
numbers.
All real
Everything.
numbers. That's why we like them so much. Right? They're our favorite class of functions because the domain is all reals. Okay, symmetry. Now, symmetry is something that you want to do relatively quickly if you can. If it's super difficult, it will take a little bit more effort, but it is worth knowing because then when you sketch the graph, if it has symmetry, you know that the shape is identical either on opposite sides of the y-axis or with respect to the origin. So this part is reflected twice. So when we look at this one, if I replace x with negative x, I get a negative x minus 1 squared, which is not going to give me exactly the same trinomial. And then a negative x plus 2 is not the same. So it doesn't look like it has any symmetry. It's going to give me an utterly different polynomial. So it doesn't have y-axis symmetry, and it doesn't have origin symmetry. This is probably the most common situation where you don't have any symmetry at all. But again, it is something that's important to look for. So we'll write down no symmetry. Intercepts. You're going to have to reach way back into your high school or early college experience and think about the algebra classes that you may have taken. And we want to think about where it crosses the x-axis or the y-axis. So it crosses the x-axis when the y value is 0. It crosses the y-axis when the x value is 0. These are interceptions of that line. So we're going to be looking first for the x-intercepts. So that means, whoa, not sure what happened there. Okay. Interesting. All right. Let's try it down here and see if that does a little better. X-intercepts, no, it's not liking it. What is that? I may need to just close and reopen the file. Looks like Word is sort of going a little crazy here. Let me reopen the file. All right, here we go. X-intercepts occur when y equals 0. Boy, I hope it's not going to do this all day today. That would be really annoying. So when we're looking at y equal to 0, that means that the equation f of x, that part of it, that expression is replaced with 0. So looking at the equation, when would it equal 0? Well, there are two options, when x is 1 or when x is -2. So we have two x-intercepts, 1, 0, and -2, 0. And then we can think about the y-intercept, which is when x equals 0. If we replace x with 0, we get the y value is equal to 0 minus 1 squared, which will give us 1, 0 plus 2, which gives us 2. So this is the ordered pair 0, 2. So we have three intercepts, two x-intercepts, one y-intercept. If it is a function, then we'll only ever have one y-intercept, but we could have multiple x-intercepts or possibly none. It just depends on the particular function. Now we want to look at the end behavior. Is it a horizontal or is it oblique or is it just approaching infinity or negative infinity? When I look at this graph, if I imagine multiplying it out, I'm going to have degree x squared from the first binomial squared times degree 1, which is x from the second binomial, and x squared times x gives me x cubed. So because it's x cubed and because the leading coefficient would be a 1, a positive 1, since it's 1x and 1x, then I can assume that it's going to follow the basic shape of x cubed, at least on the edges. In the middle, it's going to look different, but on the edges, it will follow that shape. So the shape of x cubed comes up from the left, and then ours is going to do something in the middle. We're not sure what it does, but it looks like that. So our end behavior is going to be the limit as x goes to infinity should be infinity, and the limit as x approaches negative infinity should be negative infinity. So we're expecting the graph to go up on the right and down on the left. We have no horizontal asymptote, the end behavior. We have no oblique asymptote for end behavior. Vertical asymptotes, we have no vertical asymptotes. Those are zeros of the denominator that do not cancel. We have only 1 in the denominator. For the same reason, we have no holes. So we're now ready to do the derivative effect on the graph. So we're going to look for critical points, which would be related to the first derivative. So we're going to look at our function, x minus 1 quantity squared times x minus or x plus 2. So we'll take a picture of our function. And we'll put it out here. There's our function. So we want to look at critical points now. Remember, there are two types. Type 1, f prime of x equals 0, and type 2, f prime of x does not exist, but it's in the domain of f. Now we've already determined that the domain is all reals. I'm not expecting any type 2s because it's a polynomial. You typically only get type 2s with some kind of root or with a quotient of some kind. Occasionally with trig functions as well. So now we want to look at critical points of type 1. Critical points of type 1 would be related to the derivative, and with the way that it's written, I'm going to do the product rule and then chain rule on the first factor. So this is going to give me f prime equal to derivative of the first factor is bring the power to the front, freeze the inside, reduce the power by 1, multiply by the derivative of the inside. The derivative of x minus 1 is 1. And then multiply by the second factor, plus derivative of the second factor, which is 1, times the first factor. So if I clean up my derivative a little bit, I have 2x minus 1, x plus 2, plus x minus 1 squared. Now, x minus 1 becomes a common factor, which I can factor out. And I do want to know where it's equal to 0. So having it in factored form would be easier to find the zeros of the first derivative. So I'm going to factor out that, and that leaves behind 2 times quantity x plus 2 plus a single x minus 1. 2 times x plus 2 becomes 2x plus 4. And then when I add that to the x minus 1, I end up with the quantity 3x plus 3. Now I can factor the 3 out of that particular term and pull it to the front. So I get 3 times x minus 1 times x plus 1. Everybody check my algebra and arithmetic, make sure I'm keeping it honest. And that, of course, is the difference of two squares. So if you wanted, you could set it equal to 0 at this point, or you could multiply it out and then set it equal to 0. So we need to know where the first derivative is equal to 0, which is easy enough from this form, which would be when x equal 1 or x equal negative 1. So we have two critical points. We don't yet know if they're extrema or not. We just know that they're critical values. And now what we want to do is we want to look at the increasing and decreasing behavior. So we're going to use our critical points to divide up the real number line into sections. So we have from negative infinity to negative 1, between negative 1 and 1, and from 1 to infinity. Choose a test point in each section. So I'm going to choose negative 2 for the first section, 0 for the second section, and 2 for the third section. What we want to evaluate is the first derivative, f prime. We want the sign of it. We don't actually want the actual number. We just want to know if it's positive or negative. So here is f prime right here. So we'll be able to evaluate. When I have negative 2, imagine trying to plug in negative 2. So you've got a 3. Negative 2 minus 1 would still be negative. So 3 positive times negative is negative. Negative 2 plus 1 is also negative, though. So I've got a negative times a negative, which will make it positive. Does everybody understand how I did that? I used the sign of each individual factor. 3 is positive. Negative 2 minus 1 is negative. Negative 2 plus 1 is negative. So I have a positive, negative, negative, which is a positive. Now we want to repeat the process when x is 0. So we have a positive. 0 minus 1 is negative again. 0 plus 1 is positive. So we have a positive times a negative times a positive, which is negative. One last time with the test value of 2. 3 is always positive. 2 minus 1 is now positive. 2 plus 1 is also positive. All three are positive, so it's positive. I like to draw the arrows to indicate whether it's increasing or decreasing. So we have increasing from negative infinity up to negative 1. So we'll make note of the intervals over which it's increasing. So from negative infinity up to negative 1. Then it's decreasing from negative 1 to 1, still decreasing, and then increasing again from 1 to infinity. So there's where it's increasing. And decreasing, first derivative is negative, is between negative 1 and 1. Then we can use the first derivative test that tells if it goes from increasing to decreasing, it has to be a relative maximum. So we have a relative maximum here at negative 1. And we'll have to find the y value. And then at 1, because it goes from decreasing to increasing, we have a relative minimum. Now, how do we find the y value at those extrema points? Again, in order to find the y value, we have to take the original function, which is right here, and plug in those values. So if we plug in negative 1, let's see if I can get the function value in and moved over. There's the function, the original function. If we plug in negative 1, we'll have f of negative 1 is equal to negative 1 minus 1 squared times negative 1 plus 2, which becomes negative 2 squared times 1, which is equal to 4. So we have a relative maximum at negative 1, 4. Our relative minimum value actually turns out to be one of our x-intercepts. When we plug in 1, because the first factor is x minus 1, we get a 0. So our x-intercept is actually a relative extrema. It's a relative minimum. That's not all the information we're looking for. In our list, we have now made it through increasing versus decreasing relative extrema, but we need to consider concavity and inflection points. So to do concavity, I'm going to take this version of the derivative, and I'm going to go ahead and multiply it out, and then I'm going to use that to find the second derivative. I've still got some space here. So our first derivative, in the last form we had it, was this. So I'm going to multiply this out. This gives me 3 times x squared minus 1, which is 3x squared minus 3. Now it's easy enough to take the second derivative in that form. You could have taken it in the first form. It would have been relatively easy as well. You would have had to use the product rule though. I wanted to avoid the product rule, so I multiplied it out. This would give me simply 6x. Now, I could have used the second derivative test to determine the relative extrema. Remember that if you take the second derivative and you plug in the critical point that's a relative extrema, if you get a negative, it has to be concave down, so it's a relative max, which does work here. And if you plug in 1, you get 6, which is positive, so it's concave up, so you got to have a relative minimum. We want to use this instead to find the places where it is concave up and concave down, and then to find inflection points. So again, we're basically looking for critical values of the second derivative. So we're looking for critical points. So we have the second derivative equal to 0. This is type 1. Or type 2. Second derivative does not exist, but it's in the domain of the first derivative. Each time we only go back one layer, one level. Now, if we're looking at this, because our first derivative was polynomial and because our second derivative is polynomial, there won't be any of type 2, which I expected from the beginning. And then if I set the second derivative equal to 0, I get 6x equals 0, which implies that x equals 0. So the only potential inflection point is at 0, but it does not have to be an inflection point. It could instead be a cusp. When you have a cusp like this, like imagine a heart shape, if you will. If you have a cusp, it could be concave down on both sides, but you could have a place where the derivative does not exist. Ours is not that way, so I am expecting this to be an inflection point. We repeat the process of dividing the number line into regions based on the critical values we found, and then we look at the sign of the second derivative. So I would use a test point of -1 and 1 into the second derivative, which is 6x. So it's negative on this side, positive on this side. So that tells me it's concave down, like a frown, on this part, and concave up like a cup on this part. So this would be concave down from -infinity up to 0, and concave up from 0 to infinity. These are super long problems. They probably will take you 2 full pages at least. And then we have an inflection point at 0. Now, to find the y value, we again have to return to the actual function, which is this value right here. So we need to come back to the original function. All points are on the original function, not on the derivative values. So we're going to put it here. Paste. So when x equals 0, we get f of 0 is equal to 0 minus 1 squared times 0 plus 2. This is going to be the y-intercept. And so this gives us -1 squared, which is 1 times 2, which we get 2. All right. You have now pulled apart this problem to the nth degree. You have all this information. So let's see if we can try to imagine what it looks like. At this point, you would try to draw a graph using all of this information. Now, in the interest of time, what I'm going to do instead is simply show you the graph, and we'll go through each piece and make sure that it does meet our expectations. So our function originally was x minus 1 squared, x plus 2. Right? Now, we're going to go through each piece and we're going to identify the different parts of the information that we have. So the first thing we have is that the domain should be all reals and it is not symmetric. We should have an x-intercept of 1, 0 and negative 2, 0 and a y-intercept of 0, 2. So we have x-intercepts at negative 2, 0 and 1, 0. And we have a y-intercept of 0, 2. We'll put labels on each of these points.
Unit Southwest.
That's from our x-intercepts and y-intercepts, which is the college algebra piece. The next thing we have is that we expected the limit, the end behavior as it goes to positive infinity to go up, and the end behavior as it went to negative infinity to go down. Let's look at the graph and make sure that it does do that. Yep, down to the left, up to the right. The next piece of information that we had was the increasing from negative infinity to negative 1 and from 1 to infinity. Increasing from negative infinity to 1 and again from 1 to infinity. So we need to add on our extrema value of negative 1, 4. We'll label that one as well. And decreasing between negative 1 and 1. And we can see it is decreasing between negative 1 and 1. So far, each piece of information that we have is matching up with the graph. We have a relative max at negative 1, 4, a relative min at 1, 0. And I'm going to make all the points black so that they show up a little bit better. And then the next pieces of information that we have are coming from concavity. We have that it is concave down from negative infinity to 0. So from negative infinity up to 0, it is concave down. So down means like this, curvature. So we've got it down from here to here, and then concave up from here to infinity. So it looks like our only inflection point is at the y-intercept, which is 0, 2. All right, so these are all the pieces of information that we have, and they match up with the graph that Desmos produced. You would probably be drawing it by hand on your exam, but this is basically what you would need to show. So here's the analytical algebra part behind everything that you did in your groups. The domain is all reals except negative 2. Thou shalt not divide by 0. Ever, 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 don't ever do it. You can do it in a limit because it's not really getting to that value. You're not dividing by 0. You're approaching, but you never get there, okay? So it's the idea of a black hole. You're forever getting closer, but you never arrive. All right, so in this case, we have 4x plus 8 cannot be 0 or x cannot be negative 2. So negative 2 is not in the domain of the original function. This one does not have symmetry. When you replace x with negative x, you get a completely different function. It's not the original, and it's not the total opposite of the original either. So it has to be totally opposite in sign, and it's not, so there's no symmetry. We do have an x-intercept. That's when the y is equal to 0 or the numerator is 0. So 3x plus 5 equals 0 gives us x equal negative 5/3. Y-intercept, x is 0. When we replace that with 0, we get 5/8. The end behavior, remember, is the limit as x goes to infinity and the limit as x goes to negative infinity. In this case, the degree of the numerator and degree of the denominator are equal. And so this gives us the ratio of 3/4. This is going to be a horizontal asymptote with 3/4, but it only applies at the ends. The far right as x goes to infinity and the far left as x goes to negative infinity. It does not come into play in the center of the graph. Vertical asymptotes, those are zeros of the denominator that don't cancel. So we have 1 at x equal -2. We have no holes because in the factored form, nothing cancels and disappears from the denominator. Now, the calculus section of this is somewhat interesting. When we look at the critical values, and you can do the derivative either in the quotient rule or product rule form. And when you do that, you end up with 4/4x plus 8 quantity squared. Well, this is never going to be equal to 0 because you have 4 in the numerator. So we have no type 1s. We do have a place where the denominator is 0, but it is the value that is eliminated from the domain of the function. So we have no type 2s either, which means we have no critical points. But when we look at this first derivative, I've got a positive 4 over something squared, which tells me that no matter what x is, it's going to be positive. And that means it's increasing over the entire domain, since f prime of x is always positive. This upside down capital A that you see right here stands for the phrase for all. So you would read that as for all x in the domain, the derivative is positive, so it's increasing on the entire domain. Then I did the second derivative by writing it in the power form. So if you look up here, I did the first derivative in the power form with a power of -2. And then I took the second derivative of it and I got -8 over 4x plus 8 cubed. Now this also has no critical points, which tells me that basically I don't have an inflection point because I have no critical points. But I do have a place that divides it, and that is the -2, which is the 0 of the denominator. So testing on the left and testing on the right, I get a positive on the left and a negative on the right, which tells me it's concave up on this section for the left and concave down on this section for the right. And then I'm able to draw a basic graph of what it looks like. Okay, looks like everyone is back. We kind of ran out of time a little bit, but it looks like the first group has got a good start, or this is actually the fifth group, Jay and Eric. They've got a good start on it. This one did have symmetry. It had y-axis symmetry. So if you noted that, you only had to graph half of it. So there again, they found the critical values, which gave them some different points. They got the x-intercepts, the y-intercept, where it was decreasing and increasing. They didn't get quite finished, but they got very close. This one also has the basic shape on it, and it's got the points marked out, and you can see there are some changes in concavity from one end to the other. They also got about partway through with this one. And Roz and Michael and Aubrey didn't quite get theirs on there, but that's okay. I didn't give you quite enough time. On this one, just running through the algebra and calculus quickly, we did have the domain of all real since it's polynomial. It does have symmetry. When you replace x with negative x, you get exactly the same function. So it's y-axis or even symmetric. We have a y-intercept of the origin, which also is going to be an x-intercept. And when we solve the x-intercepts, we also get plus or minus root of 3/2, comma 0. The end behavior, because it's a polynomial and it's degree 6, it's going to go up on both ends like this with some changes in the middle. Because it's not a rational function or the ratio of two functions, we have no vertical asymptotes and no holes. We also can find the critical values of the first derivative by setting the first derivative equal to 0. Here's our first derivative. There are none of type 2 because it's polynomial, so it exists everywhere. And this divides up the real number line into 1, 2, 3, 4 sections. But again, we have symmetry. So you can see that we've got some symmetry going on, and we've got some increasing and decreasing behavior. So if you look at this right here, you can see that it is increasing from -1 to 0, and again from 1 to infinity. It is decreasing from -infinity to -1, and again between 0 and 1. We have a relative minimum that is symmetric on either side of the y-axis. That's -1, -1, and 1, -1. And we have a relative maximum of 0, 0. This is a lot of information, which would give a good graph, but without concavity, it doesn't give a great graph. So the next thing we look at is the second derivative. And when we factor the second derivative, we get 12x squared times quantity 5x squared minus 3. Again, it's polynomial, so it exists everywhere. So there are no type 2 critical points. When we set the second derivative equal to 0, we again get 3. And that is 0 and plus or minus the square root of 3/5, which is about 0.77. So I took test points of -1, -0.5, 1/2, and 1. And I plugged those into the original values. And I found that it was concave up on 2 sections. And again, I've got symmetry going on here. And then I've got concave down on these 2 sections. The only thing I didn't manage to find were the 2 inflection points. I hadn't gotten quite that far yet, but we can find the 2 inflection points by taking the values of negative square root of 3/5 and square root of 3/5 and plugging them into the original function, which I believe the original function was 2x to the 6th minus 3x to the 4th. So this is our original function. And then we've got symmetry going on. So we can expect to get the same value for the square root of 3/5 and negative square root of 3/5. And when we plug those into the function, we should get, you can do square root of 0.6. That will give you the value. Raised to the 6th power equals times 2 equals minus 3 times the square root of 0.6, to the 4th. Hopefully this is going to calculate it correctly. And I got -81 over 125. So this is about plus or minus 0.77. And this one is about 0.648. So looking over here, we can see the inflection points and the changes in concavity. So if we wanted to put on one of those, we could include the square root of 0.6 or 3 divided by 5, come out, comma, and then I believe it was -81 or -0.648. Right? And we can label that. That is the change in concavity right there. And we've got another one, which is going to be where it's negative. We've got the x-intercept. The y-intercept, of course, is the 0, 0. And you can see the pertinent parts of this graph. So we should also add the third one here, which is going to be at the origin, which is 0, 0. And we should probably make all of these darker so that they show up. So I'll make them all black. And then I believe we also had some x-intercepts. So let's add our x-intercepts onto the graph, make sure that we have everything that was important on the graph. That was the square root of 3/2 0 and negative square root of 3/2 0. So I can change the 5 to 2. And this was 0. We'll make it black as well, so it shows up better. And this is the other one, which is symmetric to it due to the symmetry. So now let's take a look and see what all we've got on here. Looks like I accidentally typed a 9 instead of a 0. There we go. So we've got decreasing coming down here. We haven't marked off our relative minimums, so let's do our relative minimums. So that would have been, let's see, we'll start at the top, make sure we have it all. We have the y-intercept and the x-intercepts, all three of them. The end behavior should be going up on both sides, and it is. And we had no vertical asymptotes or holes. Critical values gave us increasing from -1 to 0 and 1 to infinity, from -1 to 0 and 1 to infinity. That matches the picture. And decreasing from -infinity to -1 and between 0 and 1. So decreasing from -infinity to -1 and between 0 and 1, that matches. And then we had relative minimums at -1, -1, and 1, -1, symmetric across the y-axis. So we need to mark off those values now. So -1, -1. And also 1, -1. Okay. And we'll put the labels on each of those and turn them darker so they show up better. And so now we've got our relative minima on the graph as well. Two relative minima. In fact, they are actually the absolute minima. And then we've got a relative maximum here. It's not an absolute maximum because the graph goes higher on both the far left and the far right. Let's see what else we can pull out of this. We had critical values, which we used to divide it up for the second derivative. And that gave us the inflection points at plus or minus the square root of 3/5 and -81 over 125. And these are these values right here. So if we want, we can look at those now. Notice that 0, 0 has showed up multiple times. It is the y-intercept, it is an x-intercept. It marked where it went from increasing to decreasing. So it was a critical point of the first derivative. It's also a change here in the graph. And so we've got all kinds of behavior going on here. So we've got concave down between this inflection point up to 0, 0 and concave down again on the other side. But because the concavity does not change, 0, 0 is not an actual inflection point. Concavity has to change to be an inflection point. So the derivative, second derivative is 0 there, but it's not an inflection point. And then we have here an actual inflection point because on the left it's concave up and on the right it's concave down. And at this point over here, again, we have concave down on the left and concave up on the right. So it actually has only 2 inflection points. Only where the second derivative changes sign do we get inflection points. And now we've got pretty much everything on the graph and it's labeled pretty well. If we blow it up a little bit, it does help to see these points slightly better. So I'm going to take a picture of this one and add it to the notes. so that we have a picture of what the graph looks like. It will make the screen kind of dark. Sorry about that. That's just the way it works when it takes the picture. And we can add the picture now at the bottom of our work, which we see right here. And we can blow it up a little bit, make it show up a little larger. Okay, let's take a look now at another example. We've worked example 1, which I did for you. We worked example 2, which you worked on your own, and then we've just gone through it again. We worked example 3. Now let's look at example 4 that has an oblique asymptote. So something we've not dealt with before in this class. I hope that you have seen one before in college algebra or in your high school algebra class, but it is possible you didn't see one. In which case, I'm going to go through this rather slowly so that you get the technique down, but hopefully this is review for you. If it's not, do come to see me during office hours. Now we have the function 10x cubed over x squared minus 1. If we write this in a more fractional form, then we have the function f of x equal to 10x cubed divided by x squared minus 1, which is the form we're most used to seeing in mathematics. When we look at it, notice that the degree of the numerator is 3 and the degree of the denominator is 2. Because the degree of the numerator is precisely 1 larger than the degree of the denominator, we have what's called an oblique asymptote. Now, what is an oblique asymptote? An oblique asymptote is basically a slanted line in the graph that might draw in the graph like an asymptote. So it might do something like this, where it approaches that slanted line like an asymptote. Now, we only call it an oblique asymptote when it is a slanted line. And that requires that the numerator be precisely 1 degree larger than the denominator. If it is more than 1 degree larger than the denominator, it won't be a slanted line, but it will still be an asymptote. It could be something more parabolic in nature or something else. If the degree of the numerator equals the degree of the denominator, then we have a horizontal asymptote, which is the ratio of their leading coefficients. If the degree of the numerator is smaller than the degree of the denominator, then we have a horizontal asymptote of the x-axis. In other words, y equals 0. In this case, it's going to be oblique. We're going to start the same way. We want to look at the domain of the function first, because anything that's not in the domain is not on the graph. And if it's not on the graph, it cannot be a critical value. It cannot be a relative extrema or an inflection point or anything else. It is not in the domain. So we're going to start with the domain. And remember, when you look at the domain, you're looking at all the values that it cannot be. In this case, because we have a fractional form, a rational function, ratio of 2 polynomials, we basically have the denominator cannot equal 0. So we've got x squared minus 1 not equal to 0. When we're looking at that, the next thing we want to do is solve this. So we can move the 1 to the other side, and we get x squared should not be 1, which basically means that x should not be plus or minus 1. So our domain is going to be all reals, but not plus or minus 1. So if we get plus or minus 1 as a critical value, we can ignore it because it is not in the domain of the function. Critical values must be in the domain of the function. Now we're going to look for symmetry. When we look for symmetry, remember that you replace the x with negative x to see if you get either exactly the same function as the original, in which case it is y-axis symmetric, looks the same on both sides of the y-axis, or it gives you exactly the opposite, -1 times the original function, in which case it is origin symmetric. So you have to do a double fold to get it to lay on top of its side of itself. So now we're going to replace x with negative x. And so we get 10 times negative x quantity cubed over negative x squared minus 1. When we cube a negative x, we still have the negative. So this becomes negative 10 x cubed over, well, if I take a negative x and square it, negative squared is still positive. So I just get x squared minus 1 back. This is negative times 10x squared, or cubed rather, divided by x squared minus 1. In other words, I do have exactly the original function, but with a negative on it. That means that it's origin symmetric. So we do have symmetry with respect to the origin. So if we have the point 2, 8 on the graph, we'll have the point -2, -8. Change the sign of the x coordinate, change the sign of the y coordinate, but their magnitudes are the same. So we do have origin or odd symmetry. Now we want to take a look at the end behavior. So I'm having trouble with writing symmetry today. I didn't quite finish my M's. All right, so now, intercepts first. So we'll do intercepts and then we'll do our end behavior. So let me copy off the function again. So I can paste the function right here. And now we want to do intercepts. So when we talk about intercepts, this is an algebra concept. We want to look for the x-intercept, which is when the y value is 0. And we want to look for the y-intercept, which is when the x coordinate is 0. So x-intercepts, we're going to take and set y to be 0. Y is the function. So we have 0 equals. Well, when do you get a fraction equal to 0? When does this fraction equal 0? Only when the numerator equals 0 and the denominator does not equal 0. So we can't get 1 or -1. So when is the numerator 0 other than at 1 and -1? So we're going to set this equal to the numerator. And of course, that just tells us that x equals 0. So we have the ordered pair 0, 0. Now 0, 0 is both on the x-axis and the y-axis. So I'm expecting to find this as my y-intercept. But we can plug it in to see. And again, this means that you take the function and you let x equal 0. So you get 10 times 0 cubed over 0 squared minus 1, which gives us 0 over -1, which of course is 0. So we only have one intercept, which is the origin. So it's both the x and the y, one intercept total. Now we want to do the end behavior again. So I'm going to paste my function up again so I can remember what it is. And I want to look at the end behavior. Now, end behavior, of course, is the limit of the function as x goes to infinity and the limit of the function as x goes to -infinity. That's what I'm looking at right here. What happens to the function on the far right and the far left? So for this particular problem, we first examine the degree of the numerator, which is 3, and the degree of the denominator, which is 2. That's the highest power on any one term. We locate the highest degree terms, 10x cubed over x squared. And when we reduce, we have 10x, which is degree 1. That's precisely 1, so we have an oblique asymptote. Now we get into the college algebra that you may or may not have seen before. To find the oblique asymptote, we need to do long division. Yes, I said that right, long division. So we're going to take our function and we're going to replace all the missing terms with zeros. So we have 10x cubed, we have no x squared term, we have no x term, and we have no constant. But again, we are taking all of the values in the dividend, which is the numerator, and we're replacing any missing terms with zeros. The divisor, it doesn't matter if we have missing terms. You can fill them in, but you don't need to. But you do need to fill them in on the numerator part. So our divisor is x squared minus 1. Just scrolling up and down to see the function to make sure I've got it right. Now we're going to apply the steps to long division, which you probably haven't done possibly since 4th grade when you learned it. So this is a really long time ago. You grew up with calculators, so you're used to using calculators all the time. So let me remind you of what the steps are. Step one, we estimate. Now, in this particular case, when we're estimating with polynomial long division, that means take the highest degree term under the division symbol, 10x cubed, and divide by the highest degree term outside in the divisor. So that gives us 10x cubed divided by x squared, which is going to give us our estimate of 10x. Put the 10x on the top as part of the quotient. Now, our next step is to multiply. And when we multiply, we use the distributive property to distribute it over both terms in the divisor. So we're going to multiply as our next step. And some students find that it's actually faster if they write more by writing it out to the side underneath the steps. 10x times x squared minus 1, and that will give them a 10x cubed minus 10x. Now, here's the tricky part. When you multiply it out, whether you write it underneath or you do it directly, you need to line up each of the like terms underneath the like term in the dividend. So then we've got 10x times x squared, which is going to give us 10x cubed. That should be exactly the same. If not, our estimate was wrong. We need to start over. This should be identical to the first term here. Then we multiply 10x times negative 1, which is a negative 10x, which I need to line up under the other x term. So I have a negative 10x here. Now, my next step to long division is to subtract. Now, subtraction with polynomials basically means change the signs and add. So when we change the signs, that means that I can come up here, I'm subtracting the entire polynomial. I like to actually physically write them because I find that I do better and work faster and more accurately when I actually write it down. I know it's counterintuitive that the more you write, the faster you go, but you're freeing up your brain to do the hard thinking by keeping track of the details on the paper. And that actually speeds you up. It's neuroscience, not rocket science, it's neuroscience. So I get 10x cubed minus 10x cubed, which of course leads to 0. And then I've got 0x squared plus nothing, which is still 0. And then I've got 0x plus 10x, which is a plus 10x. Sign goes with it. Now, the next thing that I should do in long division is I would bring down. So that's step 4. All right. So the next thing I'm going to do is bring down the plus 0. Now, normally you'd start over again with estimation. So the rule is repeat until the degree of the subtracted part is less than the degree of the divisor. And we've already got that situation. When you're looking for an oblique asymptote, it's generally 1 or 2 steps at most. It doesn't take very much. So how do I know to stop? I've got 10x in the subtracted part, which is degree 1, and the divisor is degree 2. Since this is a lower degree than the divisor, I stop. And so my remainder is this 10x. So I have 10x plus 10x that never got divided by x squared minus 1. That's my remainder. Do you remember remainders way back, 4th grade? I know memory's kind of dim for me. It was like decades ago. So if you can remember back there, the numerator is the remainder and it never got divided by the divisor. And so this is what we have. Now, what is the oblique asymptote? The oblique asymptote, which is that slanted line it gets close to as it goes out to positive infinity and negative infinity, is actually the quotient part, which is the part without the remainder. So my oblique asymptote is actually y equals 10x, that line right there. So that's coming from this part right here that I've highlighted in yellow. So this becomes the oblique asymptote. It omits the remainder divided by the divisor. That's not part of the oblique asymptote. So we're going to graph the line y equal 10x as a dashed line with dashes or dots, and that will become our oblique asymptote. All right. Now let's put onto our graph what we've got so far. We know that we have a y-intercept and x-intercept of 0, 0. So I'm going to put onto my graph the point 0, 0. And I'm going to turn it dark so it shows up better. So I like to use black or blue. Those two colors tend to show up well. So I've got that on there. And I know I have y equal 10x. And I want this to be an oblique asymptote. So I'm going to make this one be dashed lines. You could use dotted if you like dotted better, but I think dashed looks better. So I'm going to use the dashed. And that's the information that I've gathered so far. Now, the next things that I wanted to look at after I looked at end behavior, and again, the end behavior is it's going to follow that line. So as it goes out towards infinity and negative infinity, it's going to try to get close to that line. So that's why I've got the end behavior. After that, I'm going to look for vertical asymptotes and holes. These are zeros of the denominator that either don't cancel, vertical asymptotes, or zeros of the denominator that cancel and disappear from the denominator, holes. If they cancel but don't disappear from the denominator, they're still vertical asymptotes. So that disappearance is important. Now we've already found them. They were eliminated from the domain that's basically x equal 1 and x equal negative 1. Now, if I factor this, I can write it down as x minus 1 and x plus 1, but those don't cancel with the numerator, which is 10x cubed. So nothing cancels. So I have no holes. So when I'm looking at this, I'm now looking at vertical, oops, maybe I should switch back to a color. So let's go with black just to provide some visual contrast. Vertical asymptotes. I've got x equal 1 and x equal negative 1. Holes, I have none. Now, if you're wondering, what does she mean by cancel? I mean, suppose you had something like x minus 2, x plus 3 over x minus 2, x plus 2. Then the x minus 2's cancel, and so the 2 becomes a hole. That's what I mean by a hole. And to find the y value, you would plug it into the remainder after you canceled out the like factor. So that's what I mean by holes. And ours has no holes because we have 10x cubed over x minus 1 times x plus 1. And nothing cancels and disappears from the denominator. Now, our next part is to add this onto the graph. So we have x equal 1 and x equal negative 1, and these are also asymptotes. So we'll make them dashed lines as well. And we'll make them the same color blue. So we're going to turn it blue and dashed, and then make this one also blue and dashed. All right, so I've got my asymptotes on here. It's looking kind of crazy. I don't actually have the graph. I have all the things it's not going to be, but I don't have anything it actually is yet other than the point at the origin. Now, what do we want to find? What were the next things in our list? We've found the vertical asymptotes and there were no holes. Now we want to do the more calculus part of it, which is the critical points, which will tell us the critical points of the first derivative give us increasing, decreasing, and relative extrema. And the critical points of the second derivative give us concavity and inflection points. So now we want to look at those. And I believe I still have the function copied. Yes, I do. So now we can take the derivative of it. I do prefer the quotient rule to using the chain rule because I hate getting a common denominator. So I'm going to do it that way. So I'm going to look at critical values or critical points. So I need the derivative. So I've got f prime of x is equal to the derivative of 10x cubed, which is 30x squared, times the denominator, which is x squared minus 1, minus derivative of the denominator, which is 2x, times the numerator, which is 10x cubed, all divided by the denominator squared, which is x squared minus 1 squared. So let's check it again, make sure we did it correctly. So I have derivative of the numerator, 30x squared times the denominator, minus derivative of the denominator times the numerator, all over the denominator squared. However you memorize that. Now we want to clean this up a little bit. So I'm going to write it in pink directly above it. Let's see if this will all go down a little bit. So up above here, if I distribute the 30x squared, I get 30x to the 4th minus 30x squared minus, and I'm going to leave it in, oh, well, I guess I only get one term, so I don't need the brackets. 2x times 10x to the 3rd would give me 20x to the 4th. And I like to write it directly above if I've left enough space. Now, the next thing I want to do is combine my like terms, 30x to the 4th minus 20x to the 4th. So my first derivative is going to be equal to 10x to the 4th minus 30x squared, all divided by x squared minus 1 squared. Now, I do want to know if there are any things that are going to cancel or disappear. So I could factor it directly, or I could wait and look at it when I'm looking at the critical points. Remember, we have type 1 and we have type 2. Type 1, first derivative equals 0, which basically means the numerator equals 0, but the denominator does not. So we have 10x to the 4th minus 30x squared equals 0. And type 2, which means the first derivative does not exist, but it is in the domain of the function. Now, the first derivative does not exist, in this case, only when x equals 1 or negative 1, but 1 and negative 1 are not in the domain of the function, so I have no type 2s. Which is fairly common. Again, type 2s mostly show up when you have a cube root or a 4th root or a 5th root, you take the derivative of it. That's typically where they show up. So when they get sent to the denominator, when the radical gets sent to the denominator, sometimes with square roots as well. So when we're looking at this one, I'm going to factor out the 10x squared. So I have 10x squared times x squared minus 30, I guess, is all that's left. Check and make sure it distributes out to give you the original. That gives me 10x to the 4th. Oops, not 33. Good thing I checked. All right, so now that would give me back the 30x squared. Now, I've got two possibilities for this to equal 0, and one of them is if x is 0. So I have 10x squared equals 0, which implies that x equals 0. Or I have x squared minus 3 equals 0, which implies that x squared equals 3, which gives me x is plus or minus the square root of 3, right? So it looks to me like I do have critical points. They're going to be at 0 and plus or minus the square root of 3. And we need to know about what the square root of 3 is so we can use a good test point. And the square root of 3 is about 1.7. So something on either side of that, 1 or 2. So again, this is approximately plus or minus 1.73 actually. So now we want to divide up our number line. Maybe I should move that down a little bit. And we want to look at where it is broken up by our critical points. So I have negative square root of 3, then I have 0, and then I have the square root of 3. So these are my places where I'm dividing the real number line up into different regions by the critical points. So now I want to find the sign of the first derivative at each of these points. And a test point here would be -2. A test point here would be -1, 1, and 2. And remember, we do have symmetry, so don't be surprised if you see some similar results popping up here, because we have symmetry in our original function, origin symmetry. So again, if 2, 8 is on the graph, then -2, -8 is on the graph. So we want the sign of f prime. So we're looking at f prime, which I guess I should probably rewrite it again, or I can just look at this factored form. F prime of x equals 10x squared times x squared minus 3, right? I like the factored form for this reason. I know that 10x squared is positive no matter what, and I know x squared is positive no matter what. So it's just going to depend on the size of the number when I square the x. So for example, when I square -2, I know the first factor is positive. -2 squared is 4, so 4 minus 3 is positive, so a double positive is positive. So I know it's increasing over that interval there from -infinity up to the negative square root of 3. So I have increasing from -infinity to the negative square root of 3. And then on the next part, I want to use the test value of x equals 0, or rather -1, between √3 and 0. So test -1. When I square it, it's positive. So that first factor is positive. When I square -1, I get 1 minus 3, but that's negative. So I have a positive times a negative, which is negative. So it is decreasing between -√3 and 0. So I have something going uphill and then coming downhill. So I have a relative maximum right there, or it could possibly be an absolute maximum as well. So now what I'm going to do, and I'll have to look for these as well. So I have a relative max at negative the square root of 3 something, and I'll have to find that from the original function. And then my next test point is 1. When I plug this in, again, the first factor is positive and the second factor is negative, so it's negative again. So it stays decreasing, but it looks like it flattens out at one moment, which means that 0 is probably a saddle point there. So we've got 0 over here to the square root of 3. And then again, when I test 2, I'm going to get a positive in the derivative. So it's going to be increasing again from square root of 3 to infinity. Now looking at the signs, this was decreasing and then it's still decreasing. So this is probably a saddle point. And decreasing back to increasing, this is going to be a relative minimum. So it looks like I have a relative minimum over here at the square root of 3. Now, how am I going to find the actual value for that? To find the actual value for that, I need the original function again. So the original function, I'm going to check, but I believe it was 10x, what was it? 10x cubed over x squared minus 1. So I'm probably going to need more space here. I'm certainly going to need more space. So my function, again, from the original is here. So plugging in, I have f of negative square root of 3, which equals to 10 times negative square root of 3 cubed over negative square root of 3 squared minus 1. Now, if I cube it, that's 3 of them in a row. So 2 of them would give me a positive 3. So I would have a 30. And then I would have another negative square root of 3 left. So the numerator would be negative square root of 3. And then the denominator, when I square it, I get a positive 3 minus 1, which is 2. So this gives me negative 15 square roots of 3. Right? So hopefully you're getting the same thing and what you're looking at. So this turned out to be roughly about 26, more or less. Now, what about the relative minimum? I can do the same thing and plug it into the original function, or I can use the odd symmetry, which says if you change the sign of the x coordinate, you change the sign of the y coordinate. So this just becomes positive 15 square roots of 3. So those are my relative maximum and my relative minimum. Let's put those onto the graph now. So we have an ordered pair, and I've already forgotten what it was. Square root of 3, 15 square root of 3. Right. And it is showing up in black, which is what I want. And then I'm going to change the signs of these. So when it becomes positive for the x, oops, this should be negative. Or wait, which sign is it? Yeah, they keep the same sign. So this one should be negative, and this one should be positive. We'll turn that one black as well. All right. Now I know that's up at 26, which I can't see yet. So it looks to me like I need to change my scale. So I'm going to change my scale and make my scale go from, let's say negative 40 to 40. I don't know if that's going to be the right range or not, but at least it's a place to start and where I can see the values. Right? So I made it go from basically negative 10 to 10 and negative 40 to 40-ish. And now I can see where I think my relative extrema are located on the graph. Now let's look at the next pieces that we want to add onto our graph. After we've done increasing and decreasing, we want to look at concavity. And for concavity, we need the first derivative again. So our first derivative is right here. So let's copy that. Right? So we don't need that part. We just want this. So this is the first derivative. And now we want concavity and inflection points, if there are any. There may not be. Remember, if it doesn't change the sign of the second derivative, it could be a cusp, right? So it could maintain the same type of concavity. It could be concave up like this, or it could be concave down where it comes to a cusp. So we're looking at the second derivative, which is going to be 40x cubed minus 60x. Now, when I'm looking at this, again, I'm looking at type 1s and type 2s, so critical points of the second derivative. So type 1 would be the second derivative equal to 0, but of course, the first derivative existing. And type 2 is going to be the second derivative does not exist, but it's in the domain of the first derivative. In other words, the first derivative at that point does exist. We always go back one level. So when I'm looking at this, the second derivative is polynomial, so it exists everywhere. So I don't have to worry about these. So there are none of this type. And then, is that really what we got? Oh, no, it's not. My bad. This is the first derivative. First derivative equal to 0. Okay. Good thing I caught that there. All right. Okay, so we're looking at the first derivative, which is here. We want to find concavity and inflection points. So let me take a look at those. We want type 1 and type 2. We're not sure yet if we have any of these. I just copied off the information. So now what we're looking at is we're looking at doing the first derivative and turning it into the second derivative. So I need to find f double prime. So I'm probably going to need some more space here. So f double prime, however you want to do it, I'm going to do derivative of the numerator, which is going to give me 40x cubed minus 60x times the denominator, x squared minus 1 squared, minus derivative of the denominator is going to invoke chain rule. 2 frees the inside, reduce the power by 1, times derivative of the inside, that's chain rule, times the numerator, which is 10x to the 4th minus 30x squared. So we have derivative of the numerator times the denominator minus derivative of the denominator involving chain rule times the numerator, all divided by the denominator squared. And when you square, it's going to be raised to the 4th power. So I'm going to create some more space because I think this is going to take a little more space. And I'm going to return this as well so I can write directly above it. Now, looking at this one, I've got x squared minus 1 as a factor that's common to both of these. I can also look at factoring out something from the 40x cubed minus 60x to see if I've got any other common factors, but I don't think I will. I could take out a 20, which would give me 20x, which would give me 2x squared minus 3. And then over on the next part, down here, I could take out a 10x squared, but that would give me x squared minus 3. So that's not the same. So I'm not going to factor out all of it. I think I will take out a 10x. And over here, I'll take out a 10x squared. So not necessarily the greatest common factor, but a common factor. So actually, I guess I could just go ahead and take out the greatest common factor. That would probably be better. So this is giving me 20x. Let me write it in a different color so we can see it. 20x multiplied by, and this would give me 2x squared minus 3 times, and I'm going to take that parentheses off, x squared minus 1 squared minus, now I've got a 2x and I've got a 2, so that gives me a 4x. So I've got a 4x and an x squared minus 1. We have to be pretty careful with the algebra. And I'm going to take out a 10x squared. So times 10x squared times, and that would leave behind an x squared minus 3, I believe. All right. So double check your algebra there and make sure we haven't made a mistake, but I think so far it looks pretty good. It's pretty nasty. Okay, now what we can do to clean that up, I've double checked it in my head. So now we're going to go ahead and proceed to the next step, which is to rewrite it again. I'm going to take out one of the x squared minus 1s now. And that's going to leave a whole lot of stuff left behind.
which leads to the expression that you see represented here above. So take a moment and write it down.
So to continue with finding the second derivative, we take out the 20x and the x squared minus 1. And that's going, or we take out the x squared minus 1 in this first step here. And that's going to leave behind 20x, which we took out of this first factor, times the 2x squared minus 3, times 1 of the x minus 1s, which got left behind, minus 40x cubed times the x squared minus 3. And we can close our bracket up here. And then we can take out the common factor of 20x, which is common to these two factors. So we have 20x times 1 of the x squared minus, or x squared minus 1s. So I'm missing my square here. That should be an x squared minus 1. So we have one of those left. So when we take out that one, the 20x, we're left with 2x squared minus 3 times x squared minus 1 for the first, minus, we took out a 20x, so that leaves a 2x squared times x squared minus 3. So check your algebra, make sure that you're not making a mistake. This one's quite easy to make lots of mistakes on. So we've got coming out of 40, 20 leaves a 2, coming out an x leaves x squared, and then x squared minus 3. Now that we have a little bit of space underneath, so we're going to go ahead and we're going to write it underneath here. We're going to multiply out what's inside of the brackets so that we can combine like terms and get a more reduced form. So 2x squared times x squared gives us 2x to the 4th. 2x squared times negative 1 is a negative 2x squared. On the inside, we get a negative 3x squared, so those combine. And then we have a plus 3. And remember to distribute the negative 2x squared over the inside. So we have a minus 2x to the 4th, which will cancel the 2x to the 4th over here. Then a negative times a negative gives us a positive 6x squared. So we have a negative 5x squared plus 6x squared. So that will give us an x squared plus 3. So our final form, simplified as much as we can for the second derivative, is 20x, x squared minus 1 times x squared plus 3, all divided by x squared minus 1 to the 4th. Now the x squared minus 1 in the numerator will cancel one of the 4 in the denominator. And so we're left with 3 in the denominator. So this gives us 20x, x squared plus 3 over x squared minus 1 quantity cubed. That is a really, really long, difficult algebra exercise in reducing. So now we want to look for the critical points of the second derivative. So we find the critical points by taking the second derivative, set it equal to 0, or look where the second derivative does not exist, but it is in the domain of the first derivative, which of course has to be in the domain of the original. And when we're looking at this, the only place that it's not defined is at 1 and negative 1, but we tossed those out of the domain a long time ago. So they're gone. So we have none of these because it's not in the domain of the function. So we have none of type 2. Looking at type 1, we're looking for where the second derivative is 0. We can just look at the numerator then, 20x times x squared plus 3. So we need 20x times x squared plus 3 equals 0. So we have two possibilities here. We have 20x equal to 0, which means, of course, x is 0. Or we have x squared, is it plus 3 or minus 3? Let's check that out again. I have written plus 3. Let's make sure that that is correct. It looks like that is correct. So of course, x squared plus 3 equal to 0 has no real solutions because a squared variable cannot equal a negative. So we can ignore those. So we've already found that 0, 0 is on the graph. We could plug it back into the original function, of course. I believe it was 0, 0. Let's go back to our function. Yes, 0, 0 was our x and y intercept. So 0, 0 is also a possible inflection point. How do we know for sure? Well, we need to take the second derivative and we need to insert test points on either side of 0. Let's put our function on there and see if it meets our conditions. Y equals 10x to the third divided by x squared minus 1. Now we've got our function on here. So it's still quite compressed a little bit. So we may want to make it go between -8 and 8, but keep the y value the way it is. So let's go ahead and do that now. So we might actually want to increase it a little bit. So we'll go from, well, actually, I'm not sure if -5 to 5 would be good enough. Let's try -6 to 6. So -6 up here to 6. So our scale is definitely not 1 to 1, but we can now see the pertinent parts of the graph. And I'm going to put the actual graph on here in a different color than the other colors we've used. So I made it red. So now when we're looking at this, we can see the different parts. So let's go through and verify that all the parts that we found analytically do fit with our graph. So we already know the domain omits 1 and -1. We know the x and y intercept is 0, 0. And we know the end behavior follows that oblique asymptote y equal 10x. So the vertical asymptotes are here at -1 and 1. And you can see that the graph is approaching those vertical asymptotes, getting close to them. It's also getting close to the oblique asymptote as x approaches -infinity. And again, as x approaches +infinity. And we have only one intercept, which is the origin. So far it meets all of our analytical conditions. And now we want to look at the increasing, decreasing behavior. We found that the critical values were, again, the origin, and then negative and positive square root of 3. And so when we looked at these, we had the different points, which divided it up into increasing and decreasing behavior, plus or minus the square root of 3. So increasing between the square root of 3 and negative square root of 3. So we can look on here. It's increasing out here until we get to that value, which is the square root of 3 right here. It's that one. And then it is increasing again from the square root of 3 out to infinity. So we have increasing on that interval. It's decreasing between -√3 and 0 and √3. So between -√3 and 0, it's going down. You can see that even though it's split apart, both sections are decreasing. They're going downhill in general. So this is also downhill. And again, it's decreasing on this interval here and decreasing on that interval there. And then we have our relative extrema, which are on the graph. And then the last piece that we added was the concavity piece, which took a really long time with the second derivative so complicated. Notice that on the left side of the graph, this is concave down. And we forgot that we have an asymptote at -1. So we need to take that into account on our concavity. So I'm going to correct this now. We're going to scoot this down a little bit. So we're going to be testing at -2, which we found was concave down. And then we have another place where the graph breaks at 1. So we need to test the concavity on both sides of that as well. So not just at the critical values, but also at the places in the break in the domain. So where the domain is not defined. So we've got this one. Now we need to know about this one right here between -1 and 0. So we can take a test point of -1/2. And then we can take a test point of 1/2 in this part over here. So when we plug in, again, whether it's -1/2 or +1/2, when you square it, it's positive. When you square 1/2, you get 1/4. So 1/4 minus 1 is going to be a -3/4. So when you cube a negative, you get a negative. So in both cases, both test points, the second factor in the numerator is positive, but the denominator factor is negative. So then we have 20x as a factor in the numerator. So we have a negative over a negative, which would make this one positive, which means it's concave up between -1 and 0. And then we'll test over here, it's going to be a positive over a negative, which means it's concave down. So we have more intervals where it changes concavity. So between -1 and 0, it's concave up. And I knew that looking at the graph because it's concave up here on this section, and then it's concave down here on this section. So something important that we've discovered is that when you have breaks in the domain, that can affect the concavity. And it can probably also affect increasing and decreasing. So we should take a look at that as well. All right. So we've now added these points in here. Now, these can't be inflection points at -1 and 1 because they're not in the domain, but it does change concavity there. Now, if we look back at our increasing, decreasing behavior, we should also divide this into regions, and we shouldn't use -1 as a test point, even because it's not in the domain. So we've got negative the square root of 3, which is -1.77. And then we're going to have a -1. So we really should be looking on either side of that. So a test point in between would be -1.5 between those two, and maybe -0.5, -1/2. And then we should do the same thing over here. We should test between, and do that. Not sure why it scrolled on me. We should have the value of 1, and we should test at 1/2, and we should test again at 3/2. All right. So if we test at -3/2 in the first derivative, the first factor is always positive. -3/2 squared gives us 9/4. 9/4 minus 3 would be negative. So it's going to be negative in here, which means that it is decreasing. And then we have the test point at -1/2, which is definitely positive here. And we find that -1/2 squared is +1/4. So that's still negative. So it did not change the behavior that we saw before, but it is broken up by the gap in the domain at -1. And we can test 1/2. 1/2 plugged in would be, the first one is always positive. 1/2 squared is 1/4 minus 3 is going to be definitely negative again. Is that correct? All right. And then at 3/2, when we square that, we get 9/4, which is 2.25 minus 3 is still negative. So it didn't change anything as far as our increasing, decreasing goes, but it did change things as far as our concavity goes. So hopefully this helps you to put some more information together and figure out what's going on. We do want to take a look at one more example.